Let's continue discussing our power series representations by Taylor series. So we are going to work with a few more questions that are asking us to first represent a function with its associated power series representation. So we have this list of useful power series that we should know, and this is the reference sheet that I've given you in the Canvas modules. Now, we also know from the textbook, we've got a few more power series representations. We've got these ones listed here, and these in the book include some of the hyperbolics, cosh and sinh. So we can use any of these power series representations now that we've derived them, either through the videos in the book, in the homework on the worksheets. We've derived these and their associated radiuses of convergence. And so we can use these to answer follow-up questions, to work with functions, use their power series representations to do things like take derivatives and integrals, and that's what we're going to look at on this video. So for all of these examples, we want to work with Taylor series, and we can use the known series, the Taylor and Maclaurin series that have already been derived, and I reference them as our useful power series, the ones I just had projected on the screen. So for example, like in this first problem, I want to find a power series representation for the derivative of the given function, f prime of x, and find the radius and associated interval of convergence. So we take a function, f of x, which is equal to sine of x squared. And so here is an example of where we know that sine of x has a power series representation. And its power series representation holds for all x. It has a radius of convergence of infinity. So what we're going to do here is we're going to start by representing the function that we have with its power series representation, and then we can take the derivative. So f of x equals the sine of x squared. And I just pulled this little recall. I just pulled that right off of the table we had projected at the beginning. It's one that we derived in class. So we are taking x squared and substituting that in to the sine of x's power series expansion. So this goes from k equals 0 to infinity, negative 1 to the k. We're plugging in x squared to the 2k plus 1, and that is all over 2k plus 1 factorial. Now I'm going to simplify that a little bit before I take the derivative. So that goes from k equals 0 to infinity, negative 1 to the k, x to the, let's use rules of exponents there, 4k plus 2 all over 2k plus 1 factorial. Now that is true for all x, so as long as x is less than infinity, or a better way to actually say that is to say it has a radius of convergence of infinity and an interval of convergence from negative infinity to infinity. So this is true for all x's, and that will hold true when I take its derivative and its integral. In this case, we just want its derivative. So now let's go ahead. We now have the power series representation. Now let's go ahead and do a little simplification. Actually, we already got it simplified. Just take its derivative. So the derivative of this function, which is what we were asked to find, would be, let's just think about that. Just taking derivatives, that would be 2x times the cosine of x squared, because I have to use the chain rule there. So the derivative of sine is cosine, and then the derivative of the inner function is 2x. So we're coming up with a power series representation for the function 2x times the cosine of x squared. So now let's take a look at the simplified version of the power series and take the derivative term by term of that guy. Let's take the derivative of the power series from k equals 0 to infinity, negative 1 to the k, x to the 4, k plus 2, all over 2k plus 1 factorial. Now, when we take the derivative, we can literally take the derivative, bring that derivative symbol inside, and take the derivative. Remember that these factors right here are just constants, so those will stay the same, and we're taking the derivative of x to the 4k plus 2. That represents the powers on x. So we end up with negative 1 to the k. We end up, when we take the derivative, applying the power rule, we get 4k plus 2 times x to the 4k plus 2 minus 1, so that becomes 4k plus 1, and that is still all over 2k plus 1 factorial. Now, That is our power series representation for the derivative, and that is going to hold true for a radius of convergence of infinity and an interval of convergence from negative infinity to infinity, because when we differentiate and integrate a power series, its radius of convergence stays the same. But we could leave it just like that. But I do notice there is a little bit of simplification that we could do. So I'm looking right here at this 4k plus 2, and I'm seeing that we could actually factor a 2 out of that, and that would leave me with a 2k plus 1, which in the bottom 2k plus 1 is factorial, is 2k plus 1 times 2k factorial. And we might want to simplify that a little bit. And so this becomes k, that's just a common factor that we could clean up a little bit. Negative 1 to the k, then the 2k plus 1s would cancel, so we'd have just 2 times x to the 4k plus 1. Now in the bottom, all that's left is 2k factorial. And we could leave it in that form. And that does make things just a little bit nicer. So that was my derivative of that function, sine of x squared. That's the power series representation. And if we wanted to, we could start writing out terms. I think I'll leave that. We did a lot of that on the last video. We could start writing out the non-zero terms if we wanted to, just plugging in our index from k equals 0 to 1 to 2 to 3 and go as far as we needed to. So that is how we could take a power series representation of a function and then use it to find the derivative of that function. Okay, let's do some integration. So for these next two problems, I actually want to approximate the following using a Taylor series. So I'm going to come up with a Taylor series for a definite integral, and then I'm going to find that value to within an error that is less than 10 to the negative fourth, or 1/10,000th. So we want to actually not just evaluate the integral, but evaluate the definite integral, which will give us a numeric power series, and then we're going to approximate this value right here, because we know that a definite integral is a number. It represents a number, a value. And so we want to approximate this value to within the actual value, because this is going to be an approximation. So to within the actual value where the error is going to be less than 1 over 10 to the fourth, 1 over 10,000. So how are we going to do that? Well, we're going to start by representing this function here, sine of x squared, with a power series. So let's start with that. It's actually the same function we looked at before when we were differentiating, but let's just redo it. So again, recalling our formula for the sine of x, and we're going to plug in x squared for x. So we're going to get the power series, excuse me, k equals 0 to infinity, negative 1 to the k, x squared to the 2k plus 1, all over 2k plus 1 factorial. And we do have to integrate that. We're integrating it from 0 to 0.2. We'll do that in a second. Let's get this cleaned up first. So you know what I actually am going to do? Because I want to work with, rather than decimals, I prefer to work with fractions. So this is 2/10, which is 1/5. So I'm going to write that as 1/5. Okay, this is the power series from k equals 0 to infinity and negative 1 to the k. Use my rules of exponents there, and that becomes 4k plus 2 all over 2k plus 1 factorial. And we want to integrate that. So just like with derivatives, with power series, we can just integrate term by term. So this whole piece here is a constant. That's the constant, the coefficients on each of the terms in the power series. So when I'm integrating each of the terms, applying the power rule to the x to the powers. So we're going to end up with, when we integrate, we're going to get a power series. Now we do have to evaluate this power series from 0 to 1/5, so we'll do that in a second. But what is the power series when I integrate term by term? Well, we still have the negative 1 to the k. When we integrate x to the 4k plus 2, the rule of power says that we increase the power by 1, so that becomes 4k plus 3. And we divide by 4k plus 3, and we still had the 2k plus 1, the constant for each term was still left in the denominator. So we still have that hanging out in the denominator. Now, we're going to evaluate that power series. We're going to plug in x equals 1/5 and x equals 0, and we're going to see what we get. So when we plug that in, this definite integral becomes the power series k equals 0 of negative 1 to the k, 1/5 to the 4k plus 3 all over 4k plus 3 times 2k plus 1 factorial minus, well, when I plug in 0, I just get the power series of 0. So that whole thing becomes 0. We're just subtracting 0. So this definite integral that I'm looking at has boiled down to the power series from k equals 0 to infinity of -1 to the k. Now the 1/5 to the 4k plus 3, I'm going to actually move that over just a little bit, is going to drop to the denominator as 5 to the 4k plus 3 times 4k plus 3 with all the other constants that are in the denominator, 2k plus 1 factorial. So I just dropped that 1/5. I dropped the, 1 to the 4k plus 3 is just 1, so technically there's a 1 in the numerator, and I dropped the 5 to the denominator. Okay, so that's what my definite integral is equal to. Now remember that this is an infinite polynomial. Actually, it's alternating in signs, plus, minus, plus, minus. This is an infinite, it's not even a polynomial, it's actually an infinite series. It's numeric now that we've plugged in the bounds. So if I want, remember the goal here was to approximate this Taylor series so that the error was less than 1 over 10 to the 5th. Well, let's start writing out a couple of terms and see what this guy looks like. One thing I want you to notice right from the get-go is that we actually have an alternating series. And way back in the alternating series section, we had the alternating series estimation. When we did estimations with the alternating series, we said that the error is always less than or equal to b sub k plus 1 if we've used, actually let's say n plus 1. If we use the nth partial sum to estimate, to approximate the actual sum, then the error was always less than the n plus 1 term. So what's super useful about that, I'll circle this as a little recall as well. Recall. What's super convenient about alternating series is if we want to use n terms to estimate the actual sum, so we're trying to estimate right here, we're going to do a little approximation. We want to estimate, if we have an alternating series, all we have to do is go until we see a term that is less than the error that we want. In this case, we want the error to be less than 1 over 10 to the 4th. So let's write out a few terms and see what we end up with. So when k is, let's see, we start this series at 0, so let's do k equals 0, k equals 1, k equals 2. I don't know how far we have to go out, but let's see. Let's see how far we need to actually go out, and we'll estimate this. You know, I'm going to move my recall real quick. Okay, so let's keep going. So k equals 0. So when k equals 0, we have a positive 1 over, now when we plug in the bottom, we end up with 5 cubed times 3 times 1 factorial. Then we get minus 1 over, when we plug in 1, we get 5 to the 7th times 7 times 3 factorial. And then when we go to the k equals 2 term, we get a positive, it's alternating series, so we get a positive 1, 5 to the denominator. Notice real quick, as I'm doing this, I'm just kind of looking at that. Notice how quickly those denominators are expanding. Watch this one. We're going to end up with 5 to the 11th. That is a very big number already before I even multiply by 11 and then multiply by 5 factorial. These are getting, the denominators of these terms are getting really, really big. These terms get small because it's just 1 divided by that denominator. These terms themselves get small really, really fast. Okay, so let's write out what each of these, because it's, you know, when they're in this multiplied, this factored form, it's a little hard to actually see what these numbers are. So let's write it out. So this is 1 over, I just grabbed my calculator, plugged these in, and I got 1 over 375 for the first term, the 0th term, and then for k equals 1, the actual second term, I got 1 over, look at how quick this became big, 3,281,000, I have to look at my notes, 250. I'm not even going to go any further because right there, notice that by that first term, that term, if we just took this value, if that was our approximation, if we just took the first term, which is the 0th term in our notation because we let k start at 0, notice that the error in using just one term, just using the a sub 0 term, the error in using just one term is less than the absolute value of 1 over 3281250, which is clearly, you can just see that bottom, that is less than 1 over 10,000. That has to be, the denominator is so much bigger. That is definitely, so it's so like, this is so mind-blowing, right? Like we only had to use one term. We only had to use one term to get what we wanted. So we only need to use one term to estimate this value. One term of an infinite number of terms. We only need to use one term to estimate the value of this integral. So we only, the value of this integral, I should say this, the value of this integral to within 1 over 10 to the fourth. That's what we're saying right there, that we only need to use one term to estimate this to within 1 over 10,000th, 1 over 10,000 of the actual value. So in fact, the value of this particular integral can be approximated if we go all the way back to where we started right there. The value of this integral from 0 to 0.2 sine of x squared dx is approximately 1 over 375. And that is within 1/10,000th of the actual value. And we can see that just using, we're putting together a lot of pieces here. We're putting together our, known power series for the sine of x, we're integrating it, we're plugging in values, and then we're going back and we're calling the alternating series estimations. In the alternating series estimations, it's the easiest of our estimation theorems because it says that if you use the first n terms, then your error has to be less than the next term from where you stopped. So if we stopped after just right there, we stopped after just the first term, then the error has to be less than the absolute value of that next term. So we literally only had to use one term to get this estimation. Okay, let's take a look at another one. Okay, on this one, we are using a binomial series because this integral, I'm going to come down here where I have more space. This integral from 0 to, and again, I prefer to work with the fractions rather than the decimal. So I'm going to go from 0 to 0 0.5, of course, is 5/10, which is 1/2. So I'm going to replace that 0 0.5 with 1/2. This is actually 1 plus x to the 6th to the minus 1/2 dx. And so that fits right into our binomial series where p is negative 1/2. So I reference this here. And this was not relevant actually so much on the last one because the last power series that we used had a radius of convergence of infinity, so we could have plugged in any x's into our integral. But in this particular case, the absolute value of x has to be less than 1, and so we, of course, can only use a power series representation if the x's we're working with are within that radius of convergence. So that is true in this case, but we would want to clarify that. This is integral from 0 to 1/2. So we're going to take this guy and we're going to represent it as a power series. And then we're going to integrate it and we're going to plug in the values and we're going to estimate it to within 1 over 10 to the fourth. Same instructions as the previous example. So this can be represented as a power series from k equals 0 to infinity of negative 1/2, choose k. Now, in this case, the x that we're plugging in is x to the 6th. So this is x to the 6th to the k. And we're going to integrate that from 0 to 1/2. So let's get this guy simplified a little bit. This is, before we integrate, 0 to 1/2. This is the power series of negative 1/2, choose k. So up above, right there in the upper corner, I have it written out. So let's start writing out, what does this guy, this negative 1/2, choose k, what does that look like when we start expanding it out using its expansion? So that would be minus 1/2. Then we subtract 1, so it's minus 3/2. minus 5 halves, all the way out until we get to minus 1 half minus k plus 1, all over k factorial and x to the times x to the 6k. Now we are going to integrate that, and when we integrate it, we're going to be integrating just that first. Just all of this is a constant, so when we integrate it, we're just going to be integrating the x to the 6k. But we'll do that in just a second, and then we'll plug in the bounds. I just want to clean this up a little bit and play with the binomial series here for a minute. Now, for k equals 0 to infinity, I look at this and I'm thinking, you know what? Let's look at this numerator. I just really don't want to write this numerator as it is. So by the way, this is minus k plus 1 half to start. And then I look at that and I see that I could factor out a negative 1 from all of those terms. So that's what I'm going to do. I'm going to factor a negative 1 and that will leave me with 1 half, positive 1 half, positive 3 halves, positive 5 halves. This term here, when I pull out a negative, will become k minus 1 half when I pull out the negative. Excuse me. But I notice that there's a 1 half in all of those factors as well. So if I pull out a 1 half, I get 1 half to the k, and that leaves me with 1 times 3 times 5 all the way out until I get to, now I pulled a 1 half out of this k minus 1 half, so I get a 2k minus 1. And that is kind of a nice little simplification that we can then work with. Because again, remember, after we integrate, we're going to be plugging in some values. And so that gives me a nice little simplification to work with. This dx is over here. This is, maybe we'll put our power series in parentheses. We still have to integrate. We haven't integrated yet. Okay, now what I want to mention is that this rule, we do have to be a little bit careful. This rule right here that I've just generated, so I generated by doing all kinds of kind of fun factoring and pulling things out, cleaning things up really nicely. This rule is not going to hold when k equals 0. So when we do this, when we're doing these algebra, sometimes we have to pull out maybe the first term or the first couple of terms if we're going to be doing this kind of simplification to work things out. I just noticed that I wrote 2x minus 1. That should have been a k. 2k minus 1. I think I was looking ahead and thinking about my x factor next. So what we need to do here with this little star is we need to pull off the k equals 0 term. So I'm going to go ahead and do that. Let's pull off the k equals 0 term, and then we can integrate this. Okay, so we have it written out now. So as mentioned before, I had to pull off the k equals 0 term. So I pulled off the k equals 0 term. I wrote it right here. So it's going to be negative 1 half choose 0 times x to the 6 times 0. So that's, of course, x to the 0. So this whole term, by the way, just becomes 1 because p choose 0 is 1 and x to the 0 is 1. So this whole term is just 1, and we're going to integrate next. So now when we integrate, we end up with x for the first term plus the power series from k equals 1 to infinity. We have negative 1. Now my little simplification works for all k's greater than or equal to 1. So this is 2k minus 1 all over k factorial, and we're going to integrate x to the 6k. So this becomes x to the 6k plus 1 using our power rule for integration over 6k plus 1. Now we need to evaluate that whole thing from 0 to 1 half. Now remember, it was 0.5, but we switched it to 1 half, and I prefer working with the fractions. So now we're going to plug those values in. So of course we have 1 half plus, and then we have the power series from k equals 1 to infinity of negative 1 to the k. 1 times 3 times 5. It's like almost a factorial, but it is not. So I cannot express this as a factorial because notice that we're going up by 2's each time, not by 1's like we do in a factorial. All over k factorial. In the bottom, I'm also going to put the 6k plus 1. And then we're going to plug in 1 half to the 6k plus 1 because we're plugging in our 1 half. Minus, and then we plug in, we get 0 plus 0 for the power series because we're well, I'll write it this way, 0 plus the series of 0. So this whole thing right there becomes 0. And I almost didn't write it, but let's write it because, of course, we're taking our difference between our antiderivative, applying our definite integral there. Okay, so let's write out a few terms now. So obviously we already have the first term, the 1/2, and we have a way to express this. So 1, and then let's go k equals 1, k equals 2, k equals 3. I don't know how far we need to go. Again, I think these are going to get pretty small. I think these terms are going to get pretty small pretty fast, like they did on the last one. But let's write them out. So we have 1/2. Now the first term, so when k equals 1, we have a minus 1. Now in the top, we will have just times 1 over, in the bottom, we're going to have 1 factorial times 7 times 1/2 to the, ooh, to the 7th. My terms are kind of big here. We had a lot going on. So let's write, this was k equals 1. We already had the k equals 0 term. K equals 2. All right. Plus, let's see what we get there. So when we do that one, we're going to get a positive. I already said that, but we're going to get a positive because we plug in 2 for k. So we're plugging in 2 for k. I am literally just taking my expansion right above here. I'm saying it verbally, but let me highlight it to show you what I'm plugging into. So we're plugging in 2, so we get 1, and then we have the first 2 factors, 1 times 3 on the top. On the bottom, we're going to have 2 factorial times, when I plug in 2 there, we're going to get 13 times, we're going to have 1/2 to the 13th power. Okay, so what does that, I think at this point I'm noticing 2 to the 13th. That is just huge. I'm going to stop for just a second because remember, we're using that alternating series estimation theorem again. Let me grab that recall. Okay, so I just grabbed that recall from our last one. What we're trying to do is we're trying to estimate the value of this integral to within 1 over 10 to the 4th. And so remember what our alternating series estimation says is if we use the first n terms to approximate the sum, then the error will always be just less than the absolute value of the n plus 1 term, the first term we leave out. So I'm looking at this and I'm thinking, you know what? I think we're getting pretty close pretty quickly. So let's actually write these out. So this is 1/2. This ends up being minus 1 over 1792, plus this guy ends up being 3 over, oh man, this is pretty big, 3407872. Okay, that is definitely going to be less than 1 over 10,000. So let's take a look at this term right here. So this term, if I were to write it in its decimal form, is going to be 0.00. Let me make sure I get the right number of zeros. 0.00008803. So this is definitely, whether we write it in its decimal form or we write it in its fraction form, this term right here, by the time we got to the third term, this was 0, first term, we had the first term, the second term, and the third term. So by the time we got to the third term, and I know it's kind of funny to say the third term when k equals 2, but it's because we started at k equals 0. Literally, by the time we got to the third term, this guy is less than, it's in absolute value, this guy is less than 1 over 10 to the 4th, 1 over 10,000. And so what that tells me, what that is telling me is that I only need the first 2 terms. So to estimate this integral from 0 to 0.5 of 1 over the square root of 1 plus x to the 6th dx to within 1 over 10 to the 4th of the actual value, we only need to use the first 2 terms. We only need 2 terms in the series expansion, because the third term is less than my error. And so using that, what we can say is that the integral from 0 to 0.5 of 1 over the square root of 1 plus x to the 6th dx is approximately equal to 1/2 minus 1 over 1792, which is equal to, I think I wrote that down somewhere, I hope I did. You know what? I don't know that I did. Let me grab my calculator real quick. Oh, no, I did. It's 895 over 1792, which is approximately 0.499. And we can say that with confidence that that is within 1/10,000th of the actual sum. This has an error that is less than 1 over 10 to the fourth. I mean, more specifically, it's even smaller than that. It's less than this highlighted value I have up here. But that is within 1/10,000. So that's the power of having it's hard to get it all on the screen at the same time. So I'll just zoom in on the part that we finished off on. That's the power of power series. The power of power series. That is the power, it's the strength of having a power series that we can use. Because look at this. We are unable to find an elementary antiderivative here, but we can estimate this definite integral with power series, and we don't have to go far at all to get pretty close, to get pretty accurate. If you wanted to be more accurate, maybe you have to add 3 terms instead of just 2 terms or 4 terms. But in the grand scheme of things, if you have you're estimating this with an infinite series, and if you only have to add up the first handful of terms to get very close estimation, then that gives us a lot of power in using power series. Okay, so that one had a lot. We pulled together lots of different pieces to answer that final question, but it's a fun one to end on for a Calc 2 problem.